Using the rational zero theorem to find rational zeros. Another use for the remainder theorem is to test whether a rational number is a zero for a given polynomial. But first we need a pool of rational numbers to test. The rational zeros theorem helps us to narrow down the number of possible rational zeros using the ratio of the factors of the constant term and the factors of the leading coefficient of the polynomial. Now consider a quadratic function with two zeros. X is equal to 2/5 and x is equal to 3/4. By the factor theorem, these zeros have factors associated with them. Let us set each factor equal to 0 and then construct the original quadratic function absent its stretching factor. So if we set x equals 2/5 to be x minus 2/5 equals 0, or x minus 3/4 is equal to 0. So we're going to set each factor equal to 0. Now we're going to multiply this equation by the LCD, which is 5. So we get 5x minus 2 is equal to 0. And then this equation, we're going to multiply that by the LCD, which is 4. So we get 4x minus 3 equals 0. So we eliminated the fractions. Now we're going to rewrite this as a function. We're going to create a quadratic function multiplying the factors. So this becomes f of x, which is equal to 5x minus 2 times 4x minus 3. And then we're going to multiply using the FOIL or however way you want to multiply to expand the polynomial to get f of x, which is equal to 20x squared minus 23x plus 6. Now I want you to look at the leading coefficient number, 20. Well, the factor of 20 is 5 times 4. And if you notice in the denominator of those two zeros, it was 5 and 4. And then look at the constant term 6. Well, the factors of the constant term 6 is 2 and 3, which is the numerators of those zeros. So again, notice that two of the factors of the constant term 6 are the two numerators from the original roots, 2 and 3. Similarly, two of the factors from the leading coefficient, 20, are the two denominators from the original rational roots, 5 and 4. So we can infer that the numerators of the rational roots will always be factors of the constant term, and the denominators will be factors of the leading coefficient. This is the essence of the rational zero theorem. It is a means to give us a pool of possible rational zeros. Now, the rational zero theorem states that if the polynomial f of x is equal to the following has integer coefficients, then every rational zero of that function has the form p over q, where p is a factor of the constant term a subscript 0, and q is the factor of the leading coefficient a subscript n. Now, when the leading coefficient is 1, the possible rational zeros are the factors of the constant term. So, for this example, it says, list all the possible rational zeros of the function 15x cubed plus 14x squared minus 3x minus 2. So we need to identify what is the constant term and what is the leading coefficient. Well, we can see here that the constant term is 2, or negative 2, excuse me. Okay, and then we can see that the leading coefficient is the value of 15. So now that we know that, we're going to then set this up as possible rational zeros. So P is going to represent negative 2. So we can see here that P over Q so the factors of the constant term, negative 2, are going to be in the numerator. And the factors of the leading coefficient, 15, is going to be in the denominator. So what are all the factors of negative 2? Well, the possible factors of negative 2 are the following. You have plus or minus 1, comma, plus or minus 2. Those are all the factors. So you can have a positive 1 as a factor of negative 2, negative 1 is a factor of negative 2. Positive 2 is a factor of negative 2, and negative 2 is a factor of negative 2. So in the numerator, we're going to have positive plus or minus 1 and plus or minus 2. Now, what are all the factors of the leading coefficient, 15? Well, those are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So those are all the factors of the leading coefficient. Now what we want to do is now we're going to set them up by dividing each numerator by the denominator. So we have plus or minus 1 divided by plus or minus 1. We have plus or minus 2 divided by plus or minus 1. Then we have plus or minus 1 divided by plus or minus 3. And then plus or minus 2 divided by plus or minus 3. Then we have plus or minus 1 divided by plus or minus 5. Plus or minus 2 divided by plus or minus 5. Then we have plus or minus 1 divided by plus or minus 15. And then plus or minus 2 divided by plus or minus 15. So now what we can do is now we can just rewrite them in simplified form. And what I mean by that is plus or minus 1 divided by plus or minus 1 is plus or minus 1. Plus or minus 2 divided by plus or minus 1 becomes plus or minus 2. This becomes plus or minus 1/3. This becomes plus or minus 2/3. Plus or minus 1/5. Plus or minus 2/5. Plus or minus 1/15. And plus or minus 2/15. So, if we add these together, we have 1, 2, 3, 4, 5, 6, 7, 8. But we have a positive or minus, so that means we have a total of 16 possible rational zeros. So, we can conclude that there are 16 possible rational zeros.